Sit down. Yes. After studying the property of light, I think our classroom is so bright. Yes. This is a continuation of the previous session. And can anyone say what we discussed in the last class?
Sir, in last class we discussed about spectroscopy and the dual nature of light.
Good. Please sit down. We discussed about what is spectroscopy, definition, and the dual nature of light. There were a lot of confusion and discussions, debates, and finally, with the help of people there, we concluded light has a dual nature. And also, we have started electromagnetic radiation, am I right?
Yes, sir.
Yes. Our friend said light is a form of electromagnetic radiation, and many of you said X-rays, gamma rays, examples for electromagnetic radiations. Can anyone remember the definition for electromagnetic radiation? What is electromagnetic radiation?
Sir,
Yes.
sir, the word electromagnetic itself is a combination of electrical and magnetic. So the definition of electromagnetic radiation is where the both electrical and magnetic waves travels in the same medium.
Okay, good. This word itself explains what is electromagnetic radiation. So electro and electrical field and magnetic field both travel together. I want to add a little word to that. Whether it is traveling parallelly or perpendicularly. Good. When the electrical waves and electrical field and magnetic field, when they travel perpendicularly to each other, that's called as electromagnetic radiation or wave. Good. Please note. If it is a wave, what is a wave? How will you observe a wave?
So the wave has to touch and diagrammatically. And this part is known as thrust, and this part is known as thrust.
Okay. So we know that a wave, usually in sea or ocean, we get a regular wave. The wave is due to wind. Usually in ocean, the wave is origin due to the wind nature. And also you refer to a word called tide and wave are different concepts we discussed in any other class. So as he said, a wave has this type of structure, scientifically we study like this. And it has a crust and so we have another question. So how will you measure a wave? What is the unit to measure a wave?
The distance between the crust and trough.
Distance between
Crust and trough.
crust and trough. So if it is a distance between crust and a trough, then shall we have this one as the wave distance? No. Then can you show me which is the length, wavelength? Distance between with two regions, we call it as the length. Distance between these two. Am I right? So seems like the distance between two crests and distance between two crests, we measure the length. Then what would be the unit for this? Meter. Only meter?
Meter, centimeter, millimeter, and
Yes, good. If it is a length, then we can measure in any form. This is the any form, which is length, kilometer, even kilometers, meter, millimeter, nanometer, micrometer, whatever way you can measure. And I want to understand another word. What is frequency?
Number of waves or number of vibrations per second is called frequency.
Number of waves or number of vibrations per. So number of wave, number of vibrations per second. Is there any unit for that? Hertz. Yes, good. Do you know who is Hertz? Maxwell is a person who discovered electromagnetic radiation. So, as you said, no definition. The definition for electromagnetic radiation and the types of electromagnetic radiation, it was discovered by the scientist Maxwell. And Hertz is a person who first time proved the electromagnetic radiation. So, to remember him, we fix a unit called Hertz for frequency. Then, if frequency and wave both related to this particular thing, then something has to be related to each other, no? So, what is the relation between the frequency and the wavelength?
Let me explain it.
Yes.
So in this case, in 1 second we have only one wavelength. And when you come to this case, you will be having 1, 2, 3, 4, 5, 5 wavelengths in 1 second. So the relation between frequency and wavelength is inversely proportional. That is, wavelength is inversely proportional to frequency, or frequency can be inversely proportional to wavelength.
Can you show it the formula lambda equal to 1 by mu? Lambda is wavelength and mu is frequency.
In this case, the lambda is wavelength and
Yes, mu. Both the symbols are mu, but frequency we use. Yes? Good, thank you. So, the frequency and the wavelength are inversely proportional to each other. So, in such case, the last class, you said X-ray, gamma ray, and few other radiations or waves as electromagnetic radiation, examples for electromagnetic radiation. Then, is it possible to arrange those electromagnetic radiations in the way of increasing or decreasing wavelength or frequency? Is it possible?
Yes, sir.
So what would be the first one? Is based on frequency or wavelength? Wavelength. Please. So you saying gamma. So gamma rays, good. It is found to be less than 0.1 nanometer wavelength. So it is a very, very low wavelength. If any radiation is having a low wavelength, that means it has a very high frequency. So gamma is having very high frequency. In the visible light, red light having more wavelength. So red light is having more wavelength, which they are violet, indigo, blue, or red light. So next one. UV radiation, good. Ultraviolet radiation, it comes from sunlight. Nanometer, good. Ultraviolet radiation, sunlight, the ozone layer protects us from this. What about the next one? Visible. Vijaya. Violet, indigo, blue, green, yellow, orange, red. All these radiation which falls under the category of yes, visible. 400 to 500. Thank you. See, the wavelength starts from violet and end with red. So red is having more wavelength, but frequency will be low. Whichever is having the more wavelength, more wavelength will scatter very less. So rate scattering law is equal to inverse of the fourth power of lambda. So scattering is very less. So red is scatter very less. So we can easily view the red light from a long distance. That's why to indicate a danger or to indicate yes. Thank you for if you want to stop, you use red. So from a long distance, we can see it without any light. That's the concept of using red light in the air zone. Very good. IRS comes under 700 nanometer to 1 millimeter. Good. Next. Which radiation? Sir, microwave is a very long radiation, no? Wavelength?
Yes, sir.
Yes. How much?
1 millimeter to 1 meter.
1 millimeter to
1 meter.
1 meter. The microwave letters are very small. It can for a long wavelength. Okay. Next. What is the next? Radio waves. Radio waves. These waves are used to communicate. Communication networks. So that's why it is very long. 1 meter to 1,000 kilometers. I think a particular radiation is missing. Only one is missing. I think one is missing. Anyone? Microwave, good. Microwave is sorry, microwave is okay, radio is microwave is that. Good. So very good. You have arranged all the electromagnetic radiation in this. But anyone say what is the velocity of gamma rays, velocity of X-rays, velocity of UV, velocity of visible? 3 into 10 to the power of 8 meter per second. It's the velocity of speed of light. I'm asking the speed of gamma rays.
Sir, it comes under the electromagnetic rays.
Good. X-rays? Very good. Explain.
Sir, for every electromagnetic rays is as like our light, so the speed is same for everything.
All electromagnetic radiation travels at the speed of light. 3 into 10 to the power of 8 meter per second. Excellent. One more question. I am speaking here. You are able to hear my voice. In moon, what happens? Why? No medium. So for sound to travel, we need medium. Okay? You said sunlight is an electromagnetic radiation. Sunlight is coming from 150 crore kilometers. Do you think it's traveling through a medium? No. So what we can say to conclude this? Electromagnetic radiation does not require any medium to travel. Good. So we will conclude here. This is the property and these are the types of electromagnetic radiation. And when this electromagnetic radiation interacts with the atoms and molecules, there may be an emission of radiation or there may be absorption of radiation. Based on this, how much frequency or how much wavelength is observed or emitted, we can analyze the nature of a chemical compound. That's why if we use X-ray, it is X-ray diffraction spectrometer. If we use ultraviolet, it is ultraviolet spectroscopy. If we use infrared, we call it as infrared spectroscopy. If we use microwave, radio wave or something else, it is called as nuclear magnetic resonance spectroscopy. So there are a lot of spectroscopies to understand the nature of the compound and the structure of the compound using the electromagnetic radiation that we discuss in our next session. Thank you.